the reason I was thinking about this is basically old material. But the reason I was thinking about it again is I've been writing a book. I'm within epsilon of finishing it. I haven't mailed it to the publisher yet, but that's the title. And so, sure, I might go, since I'm the first speaker, I might even tell you a definition of polyhedral product, which everybody should know. And then I'm going to talk about graph products and generalized graph products, which are less well known. Right angle Coxeter groups are examples of graph products, and right angle buildings arise from graph products. Let's do right angle Artin groups. That's most of what I want. Okay, so I'm 5 minutes after 10. So I'm hoping to have time. I always felt like there's a big analogy. Well, I also want to say what a simple complex of groups is, which has to do with Wrightson and Heffliger. And but all three of these topics with right angle things have analogs with general Coxeter groups, general Artin groups, and buildings. These three things are all similar. Maybe I'll just say a word now. In every case, associated to an Artin group or a building, there's a Coxeter system. All these three things act on nice complexes, the development of the simple complexes of groups, Artin groups, and they all have the same fundamental domain, which is the same as the fundamental domain for the Coxeter group. And the buildings and general Coxeter groups act on something it's cat zero. The Artin groups act on what's the Deligne complex is, and that's the big unanswered question, is whether that's always cat zero. So I'm okay. So the reason at the end I have some description, which is, I think, analogous to the way I'm going to describe graph products acting on polyhedral products. Okay, so let me set up a little very little notation. I probably won't do enough notation. Can you write on this block? I don't want to, but maybe you can. So I want to let L1 just be a graph, a simplicial graph. And then there's an associated Phi complex where I fill in all the clicks, all the empty simplices. I'm also going to use the notation S of L to mean the set of simplices, or the set of vertex sets of simplices. So including the empty simplex. So this is basically a set of simplices in L. Oh yeah, and also I'm going to use I just to mean the vertex set of the graph. L. Okay, so let me see if I can. This is always sort of a tricky definition. Tony Barry's always yelling at me. I want to give the quick definition of polyhedral product. This is one reason I should be going for. I can be going first. So the data for this is I have a space A sub I, a subspace B sub I, and a base point in B sub I. And these are all indexed by the set of vertices. So I have this whole collection of these triples, space, subspace, base point. I don't know what the right notation is. I don't think the other guys do this, but Peter Croppoler convinced me for a while to write. So you actually have this collection of these things, pairs of spaces, and I should really, he says, just put something like A sub I, B sub I, upper L to mean this is what I'm going to define. That's the polyhedral product. Maybe I should put some more brackets around that. But sometimes we just call it as Z sub L or something. But anyway, what is this thing? So the definition is it's a subspace of the direct product of the A sub i's. So it consists of, points whose ith coordinate is lies in A sub I. So it's a set of points X sub I, where each of these X sub i's is in the direct product. And so that for each of these, this is a point X. These are points in the direct product. So that if you look at the set, if you look at the set of I, of indices I, such that X sub I does not lie in the subspace. It's a weird way to say things again. This is a simplex. These indices are the vertices of a simplex. The way I used to always think of this is that basically this meant for each simplex, you have the direct product of, this meant the product of the A sub i's and the simplices in the vertices of the simplex. And then you had the B's in the complementary set. So you had pieces like that, and you take the union. You basically take the union of those. That's what the polyhedral product is. Now, there's a tight relationship with this to buildings and graph products. I think I just want to say, since people should be knowing the generalization of this to something a little more general than graph products, generalized graph products. So here's what a generalized graph product is. Now I have a discrete group indexed by I. And I also have set EI with a GI action. So I have a GI set. And maybe is this, I have one of these for each I and I. So this the standard examples are, you could think of EI as just being GI itself, being acted on by translation, or EI could be, well, in main cases, it's just one orbit. It's GI mod HI, okay? Could be more than one orbit. But this leads to the notion of a relative graph product of Januszkiewicz and Swiatkowski. Okay, so the way I like, in this generality, it's just as easy to describe what a graph product is without writing down generators and relations or anything like that. Very topological definition of it. And so what you do is you start with this polyhedral product. You start with this AI, BI. What am I saying? You don't, that's later. You start with the cone on this GI set EI. And the second thing in the pair is this EI, which is disconnected. Okay, the cone is contractible, the EI is disconnected. And you form the polyhedral product of those things. Sometimes I think Tony Berry always wanted to call these ZL. Maybe I will too, because it's easier just to put a tilde on that. Now, the easiest definition of a graph product or a generalized graph product in this situation is if I have this polyhedral product of these sets with a GI action on it, on each of them, and it's this polyhedral product is not simply connected. It's not simply connected, for example, in the case of each of these EIs was Z mod 2, then the cone on 2 points would be an interval, and then this thing would be a cube complex, which wouldn't be simply connected. Its universal cover is the Davis-Mousson complex for a right angle Coxeter group. That's the idea that you should keep in mind. So in fact, that's the easy motivation for the following definition. What the graph product is, this thing is not simply connected, as you can, for most L, because of the fact that these EIs aren't connected. Okay, there's something like GI mod HI. So what you do is you form the universal cover. And then the graph, what I'm calling the graph product, gamma sub L, or generalized graph product, is the group of lifts. So it's the set of all lifts of the G action on Z sub L to the universal cover. What's G? G means the product of the G sub i's. So that acts on everything in sight. That acts on the product of these cones, and this is an invariant. This subspace is stable under that action. So G acts on everything, and this is the set of lifts of the G action. G means this direct product to the universal cover, Z sub L. Was that clear what that means? So the case I always thought about was if you just took a direct product of cyclic groups of order 2, and that's a simple right angle Coxeter group, a finite right angle Coxeter group, you make this construction on this subcomplex of a cube, and then you take the universal cover, and the group of lifts is exactly the right angle Coxeter group. That's the way I like to do it. There's another way to say this in terms of generators and relations, or in terms of direct limits of simple complexes of groups. So associated, without talking about universal covers or anything, I can talk about a simple complex of groups, namely, so I'm going to roughly define this. I'm going to define a simple complex of groups as some sort of post set of groups indexed by, it depends. I'm always confused whether you just say the post set of simplices or the dual to the post set of simplices. The official definition is the dual, but anyway, it's indexed by a post set. And the definition of these G sigmas is that they're the product of, maybe I'll introduce a different letter, Ji of sigma, going to be the product over all indices I, and Ji of sigma is either, so I'm just doing this in the case where EI is one orbit, GI mod H. So I have a pair of groups. So JI of sigma is either equal to GI if I is in sigma, and it's equal to HI if I is not in sigma. So each factor, you just take it. So this is supposed to give me a collection of groups. I just get I forgot to say over here, at the end result of this business of the universal cover, I don't know why I forgot to say this, is that what you have is you have a short exact sequence, which goes from 1 to the group of lifts to the fundamental group of the polyhedral product. And then it goes to the product of the GIs. And in fact, if you think about this for a minute, this gamma L is the kernel of the map from the universal cover to G. And it's easy to see that that's a fundamental group of a graph of basically something like some sort of join of the EIs, polyhedral join of the EIs. So it's a free group. Now, what's the so this thing now gives me this post set of groups. So this is a simple complex of groups. And
Sorry, Mike, that's the other way around, isn't it? The fundamental group's the kernel one. Yeah, that's the big group.
yeah. Well, I get a lot of things mixed up like that anymore. I forgot to put it up. Right, gamma sub L is the group, is the big group. It's a group of lifts. And this thing is a free group. Thank you. Now, in fact, now I just want to say the other definition of gamma sub L is it's just the direct limit of these G sub sigmas. In fact, it's really only necessary to work over the one skeleton. So for example, let me just do a ridiculous example. So for example, suppose L is just 2 points. L1 is just 2 points with 2 vertices, 1 and 2, no edges. So then I have one vertex, 1, another vertex, 2. For 1, I have the group G1 cross B2. Okay. And for 2, I have the group B1 cross G2. And over the edge, or B1 is H1, H2. And then over the edge, I have the product of the 2 smaller groups. So if, if H1 and H2 were trivial, this would just say you have gamma sub L is just the free product of G1 and G2. Otherwise, it's this slightly different free product. I think that's, now there's a big relationship of these two things to, so in other words, when we leave out this edge, if you had G1 cross the identity and the identity cross G2 amalgamated over the edge, you're just taking, then this, you have the map of the free product to the product, and the gamma sub L is just the kernel of that map. That's typically how you should think of it. Now, what's the okay with that so far? Now, Made for shorter. Now I want to talk about, it turns out that with this definition, if you take any polyhedral product, its fundamental group is a graph product. That's point number one. That's one theorem I want to say. And so what do I want to say? So now suppose I just have a pair of spaces, AI, BI, and base points, I in the index set. And then I'm going to say that I'm going to give the simultaneous proof of these, but the first theorem is okay. So how do I get one of these EI sets from that? So I let the fundamental group of AI be GI, and the relative fundamental group AI, BI, I'm going to call that EI. So the EIs come about from these relative fundamental groups. And then theorem one is if you take this polyhedral product, any polyhedral product at all, over all I, and you calculate its fundamental group, that's this group gamma L that I just defined over there. I'll sort of indicate the proof of that in a minute. So these generalized graph products come up as the fundamental group of a random polyhedral product. And the other place they come up is if I take this, we have this k pi 1 conjecture in the problem, which I didn't write down, but it says if you take a simple complex of groups and you amalgamate classifying spaces according to that simple complex of groups, you should end up with a k pi 1. This was the original question that Stallings and Gersten were working on with triangles of groups. So for this graph product complex, there's a I'll just say this is theorem 2. It says now suppose we're in the case where AI is the classifying space of a discrete group, and BI is the classifying space of a, I think it's important to say proper subgroup. Okay, so HI subgroup of GI. So BHI is a subcomplex of that. And then the second theorem is, well, what corresponds to, this says for this system of groups, which I wrote over there someplace, that simple solution, the k pi 1 conjecture has a positive solution. Okay, and so it says basically, it says if you take these BGIs, subspaces BHI, and you amalgamate it over L, I mean, you take the polyhedral product over L, this space is a classifying space. Classifying space for what? The thing that has, this is its fundamental group. This thing is aspherical, and its fundamental group is gamma. We just saw was gamma L, was a generalized polyhedral product. So this gives a positive answer for some k pi 1 problems. And maybe just, let me sort of indicate, the proof of theorem 2 is really the same idea as the proof of theorem 1. So let me just indicate the proof. I'm not going to say much. So here's sort of the proof of theorem 2. I mean, this is, at least, here's the point. If I look at if I take this BGI, take its universal cover, that's contractible. it's EGI, right? So in this case, if I take, maybe I call it AI tilde, which is really BGI tilde, this is contractible. And if I look at BHI, or this BI, in other words, BHI. So by this, I mean, I don't look at just, let me say, if I take BI tilde to be the inverse image of these things in AI tilde, it's a collection of contractible spaces, okay, of copies of the universal cover of one of these BIs, since fundamental group injects. So this is this means the inverse image of BI in AI tilde. So now I claim this thing looks a lot like what I was talking about before. Namely, if we take AI tilde, comma BI tilde, this is in either case, not just necessarily this, the classifying space case. And I take the polyhedral product of that, that's obviously a covering space of AI BI. The L. Because each of these pieces covers the corresponding factor over here. But it's not simply connected. It's not the universal cover, even though AI tilde is the universal cover. You could think about the case where, say, AI was a circle and BI was a point, then you would get AI tilde as a line, but BI tilde would be a copy of the integers. Okay. And so in that case, this thing is polyhedral product of copies of R, comma, Z has a big fundamental group. Free product of Z's or something. Okay, so so this is a covering space. It's not simply connected. On the other hand, it's obviously closely related to what I wrote down before. If I take the cone of these AI tildes, which are so here, that as I said before, the group was basically GI mod HI. I'm a GI mod HI or EI, since I wrote before. So this piece, these AI tildes are contractible, and these BI tildes are homotopy equivalent to this set, to GI mod HI. This is homotopy equivalent to a discrete set. So this is homotopy equivalent to that. Okay. Maybe not G. So this polyhedral product is homotopy equivalent to this cone, this contractible thing with these cosets. If I call that ZL, and then I take the ZL tilde, that would be so the ZL tilde, I should have said, that's an example. That's obviously, so this space is clearly non-positively curved, and the ZL tilde, this is a non-positively curved cube complex, and ZL tilde is cat 0. So in other words, I'm saying that in this case of the K-pi1 problem, this partial product has universal cover, which is homotopy equivalent to a cat 0 cube complex, and that's why it's then there's a little bit more to do, but that's the main step in proving these K-pi1 conjectures, is to prove that this that this if this space is contractible. That's the right angle building. Then you do the Burrell construction on that. Yeah.
What goes wrong with HI equals GI? Then the polyhedral product is just a product of the classified spaces. That's not B gamma L in that trivial case. The question is, what goes wrong with HI equals GI?
In this P, okay. If HI is equal to GI, then this thing is just a copy of the fundamental domain, which isn't, it's not CAD 0. I mean, it's not low, it's contractible. And I guess there's no unit there. I'm not sure what goes wrong.
Okay.
But no, something goes wrong. In this case, in the case where HI is equal to GI, it's not a building. It's a building is supposed to have two things along, at least two things along each face. This only has one, and CAD 0 fails for that.
Okay. Plus the polyhedral product's easy to write down. It's just a product of the two genes. Yeah.
This is, I wrote a paper with Peter Krafthauer correcting some mistakes in an earlier paper, and this was one of the mistakes. Was what went wrong with GI equal HI. Okay. That was his question. And we ended up writing a 5-page paper. Okay. Okay, so good. And now let me say it. So let me just remind you what we did here. What we did here with polyhedral products, how we formed the graph product. We took there were really two steps. The first step, so in doing this with the graph products, there are really two steps. Step one was somehow we looked at the cone on these EIs, cone on GI mod HIs, on the EI, and we took the polyhedral product of those things. And that turned out to, and then the thing that corresponds to buildings or Davis-Mousson complex or anything, then, so the step one was to form this polyhedral product, and step two was to take the universal cover and get some, go from non-positive curvature to CAD 0. Now you can do something like that in greater generality with Coxeter groups, Artin groups, or buildings. Okay, so in reality, what we started with here, what we started with here was the group was G, which was just a product. In the case of Coxeter groups, just a product of Z mod 2s. So that's and that acts on a cube. That's an example of a spherical building, finite spherical building. So what we want to do here is so the level of now we want to start with a Coxeter system. Yeah, I'm going to call it W prime in a minute. We start with a Coxeter system. So this means the relations aren't generated, they don't commute. You have braid relations between two. They're involutions and they have braid relations. Then you form this simplicial complex we call the nerve, and you take the fundamental domain, which I'll call K of WS or K, which, if you like, it's the geometric realization of set of simplices in the nerve, or maybe in the opposite thing for that. So this is the same, and then And then to form the Deligne complex, you look at the Artin group generated by S. You look at the Artin subgroups generated by subsets. That gives you an Artin group, and you have these cosets of the form A comma A sub T, and in this fundamental, and you paste those together via K. And that gives you the Deligne complex. It's also how you get a building. So the way you get a building let me call this W prime, because I'm going to think of this as a finite group. W prime is a Coxeter system. And now I'm going to form a new Coxeter system. By changing some of the Mij's to infinity. So you have the product of the relation of a generator corresponding to I and generator corresponding to J is supposed to have order Mij. You change those to be infinity, to be no relation. That gives you a new Coxeter system. Okay, so we get a new Coxeter system, the same set of generators, which are called WS. So in the case we were. So in the graph product case, we start with a product of Z2s. We change we ignore some of the commutation relations. That gives us a new Coxeter system, which is a right angle Coxeter group. And now buildings have the same general idea. So to define a building, so the upshot of this is, I think one good thing about this, doing this version of the polyhedral product construction, is it gives you, for Coxeter groups, right angle Coxeter groups, it didn't give you anything new, it just gave you right angle Coxeter groups. But I think this is going to give us some buildings which you don't have any other easy construction of. So I usually just use the notation script C for a building, where really I just mean it's a set of chambers, a set of fundamental domains, copies of the fundamental chambers in the building. So a building has some extra properties, might be defined by a group acting chamber transitive, but basically it's defined by you have the idea of when two chambers are adjacent to each other, or I adjacent. In the Coxeter group, only two chambers can be I adjacent. In a building, you can have more than two. And so now we have, so say if I take if I'm going to use, say C prime is going to be the chambers in a building of type W prime S. Could be a spherical building. Now this W prime S has a fundamental domain, which I'll call K. So if you take C prime meaning you take this set of chambers and you glue copies of the chamber corresponding to this Coxeter group, which I maybe should be calling K prime. So this just means you take these set of chambers, you take this. So this just means a discrete set or something. You take this model chamber right here, and then you paste them together along a codimension one face with two of them are equivalent. That's what I call, that's the standard realization of this building. Could be a spherical building. And now in the situation I'm talking about here, where I've changed the Coxeter group, maybe I should where I've changed some of these MIGs to be infinity, I have fewer simplices. So I have a subcomplex. So in other words, this new Coxeter K is the subcomplex of the original one. Like this could have been, a cone on a simplex, and this is a smaller one. So this is something like the smaller complex for the graph product. So so this is the definition. And now, so this would correspond, if this started out as being a product of Z2s, this would just be a cube, okay? And now, to form the graph product, what we do is we take this subcomplex of a cube, corresponding to this smaller fundamental chamber. We throw away some of the faces. So contained in here, so this thing is, this is CAD 0 or something. This is a spherical building. And to okay, then to so then to do what we did with the graph product, we take the same set of chambers and we replace it by the smaller fundamental chamber and glue them together the same way, okay? So this is analogous to taking this, subcomplex of taking this thing I called Z sub L. This is no longer simply connected because this is a smaller subcomplex. So the point is,
Those aren't equal.
right. This is a subcomplex of here. This is CAD 0. This is not. This is like some skeleton of it. But now what we should do by analogy with graph products is take the universal cover of this. Okay, so now take the universal cover. So it's going to be something, the chambers are still going to look like that, but there's going to end up being more chambers. Or you could think of them as just being the centers of the lifts of the centers of these chambers. The lifts of these chambers. This thing looks like an abstract set cross K. And then you just, but it's not simply connected. You take the universal cover and it gives you some new thing, C, which is the set of chambers in a building. So C is this thing was still non-positively curved locally, and this thing is now CAT 0. And in fact, you can, whatever the properties are that define a building, you can prove that this thing divided by the same equivalence relation, it's the geometric realization of a building. And the chambers are now called, or a bigger set of chambers. So let's see, in the case of right angle building, this thing was product of Z2s. This was a right angle Coxeter group. The C prime was gotten by, but was basically a product of these cones. Was the collection of products, and this was the thing we called ZL, and now you take the universal cover. And okay, let me just mention kind of. So this gives us, I mean, I think you might be able to do this all by simple complexes of groups. People have done that. But the point is that unlike the right angle case, it's hard to say what all the possibilities are for buildings. Okay, what are the buildings? What's the local structure? What buildings can occur? What what is the local structure of a building? Well, one thing that should give you pause is that they're not all, at least if we talk about thick buildings, they're not all. You can't get any possible MIJs. You can't, in just for the associated Coxeter group, you can't get any possible finite dihedral group. Like there's a famous theorem of White and Thompson that if you have a Fight and Hickman, that if you have what's called a generalized polygon, which means a one-dimensional spherical building, so that just has one, well, yeah, it has one MIJ, and it says that this M, which is MIJ, it can only be 2, 3. This is a thick spherical building. I mean, there's at least 2 panels coming off of each face. It can only be 2, 3, 6, or 8. You can't have any 5, 7s, or 17s. They just don't occur in buildings. And secondly, so this is saying there's some restriction on the Coxeter group. And there's also restrictions on the number of things in these GI mod HIs. Like for most of the, so what the situation of buildings is, these right angle buildings are more or less just as I described, they occur all the time. The other spherical buildings, the other finite things arise from algebra. They arise from finite simple groups, or they arise from, buildings over finite fields. There's some finite field, which is a prime power order. And so in particular, the number of things in GI mod HI often happens to be the number of things in a finite field plus 1. Okay, doesn't have to be that, but that's what it is for the regular things. And these MIJs always have to be 2, 3, 4, 6, or 8, or infinity. Okay. And so they had these constructions of finite buildings. And there's also some horrible business called Katz-Moody buildings, which involves constructing Katz-Moody groups, which nobody except Tits understood. And so they give you a lot of examples like this. But this new method, my book, I put a lot, you get a lot of well, you still have this restriction on the MIJs, but in fact, this thing is often has to look like the order of a finite, or it has to involve some Q, where Q is the order of finite field plus 1 or something like that. Maybe Q squared plus 1. So it's in some prime power order. In the buildings that you can construct by this method, unlike the Katz-Moody method, you can get that the number of panels along each wall can involve completely different primes, for example. And anyway, I'm not gonna, you can fool around with it and get a lot of new examples by starting with some finite Coxeter group, some spherical building corresponding to a finite Coxeter group, and then changing some of the numbers to be infinities. Then you get something, you can, start with simplex on 5 generators and erase some of the diagonals until you get something that's only connected. So it gives you a pentagon connected by 5 edges. It corresponds to some Katz-Moody group. And so it's unclear which of those, anyway, that's what I wanted. I've been wanting to say that for a while. I might have, but I put this in, this is going to be in the book. It's also in the paper I wrote like 11, maybe I wrote it in 2010. Okay, but
So,
it just says there's this other construction, which is, it's morally like taking graph products gave you a new way to, it doesn't really give you a new way to construct cat zero spaces.
so did you say you can have some of the chambers coming together, which are built from different finite groups of different prime orders?
Yeah,
So what happens when you have different prime orders coming?
well,
together?
maybe what you have to do, I mean, maybe the examples I put is you want to make, if you want to make them go, be a polygon of groups or something, you should make every other one be the MIJ be a 2. So you can have prime order over this vertex. And then prime order of an adjacent vertex, but they can mute like in a right angle. And
So there's sort of restrictions how
and
the
then you
chambers
have-
come together. It's not.
well, at least that's the examples I had. Yeah,
Thank you.
yeah. I don't know any. Right, if you want to do spherical buildings, I mean, they all have to involve a finite field. A single finite field, if you want to
That's-
do
that was my
a generalized polygon or
Right,
something.
okay, that answers the question. Thank you.
Otherwise, you have to put in some permutation relations.
Okay.
Yeah, that's all I want to say.